Thank you. Thank you, everyone. Glad to meet you virtually, and thanks for your interest in my presentation. And the title of my presentation is a bit longer than the one you saw in the program, I believe, because for this, I really want to kind of like focus on a few of the specific issues about you may actually encounter when you calculate the carbon intensity and the minimum factors for like bioenergy, biofuel, and bioproducts, and try to introduce you some of the recommendations. And also, as Greg mentioned at the beginning of his presentation, the scope, if you look at kind of like whole supply chain of the bioproducts, the scope of my talk is primarily going to be focused on what we all call gate to grade, right? So it's mostly focused on when we get a fiber, how we're going to transform this, how we're going to use it, and how we're going to basically treat it at the end of life. So when we talk about, like a carbon intensity displacement factor, I think naturally we'll think about LCA, lifecycle assessment. And lifecycle assessment is a very comprehensive tool. People use it because, it can holistically look at the product's entire life cycle and like estimate the impact from, different stages. But there's a but, right? So if you look at many of the LCA results for, let's say, biofuels, this is a review that's conducted for bioethanol from different feedstocks and also biodiesel from different oil like crops and mostly oil crops. And at individual like box here, let's say if you look at the very left, here is the corn ethanol, where the authors basically review 8 articles, and within 8 articles you have 16 different case studies in there. And as you can see, you already see a very large variation in the global warming potential, which basically your kind of like carbon intensity you're looking at, right? And there are many reasons, many like causes contributing to this variation, and we're going to cover some of them. And similarly, if we look at biochemicals, we see similar pattern, for example, for the lactic acid. Ideally, we want to see those color are all like a bluish, right? So because if you look at the legend, the bluish is like bio-based solution technology of feedstock is actually better than a fossil-based. But if we look at the places where we have multiple LC studies, usually the more studies you read, you will have like a more diverse answer to a question whether the bio-based solution is actually better than the fossil-based solution. And in this case, out of the 11 studies, you see kind of like a polarized result for the particular steps of making lactic acid. So to complete the sentence here, LC is a comprehensive tool, but variations in results often lead to inconclusive statements. So this is actually the topic I'm going to cover during this presentation, is to actually introduce you some of the key causes of variation. And this list is by no means a complete list. It's actually quite short list. But here I just list a couple of like commonly seen causes that you may actually encounter when you do your own calculation. So we're gonna first start with allocation. So here is a very quick illustration of what allocation is. So if you're familiar with LCA, that should be pretty straightforward to you. But even if you're not, it's really kind of intuitive, right? So let's say we have a product A that we want to produce from a production activity or production process. And then at the same time, we produce some intermediate product Q, which requires some treatment before it can be a marketable co-product here, right? So in this case, we have 2 processes. One is the production, and the other one is the treatment. Then each process will incur like energy use, materials, waste generation, right? Those are the things you want to account for. And then how are we going to do allocation? This is conceptually is that you will have the impact, right, from these 2 steps, and then you before you allocate that, it's basically just kind of like merge together. And then based on certain criteria, you're going to see a lot of criteria, a lot of options you're going to see in the next slide. You can allocate the impact to your main product. In this case, is product A, and your co-product, which is product B. So just to give you a more concrete example, this is a lignin boost process, right? So for extracting lignin and pulp from, let's say, like crafted pulp mill here. And then let's say we have 2 products. One is lignin, one is the pulp. Right? And then how do we how do we calculate the carbon intensity of the lignin we get, right? So this is the result from that particular figure I just showed you in the previous slide. That's a review study looking at the different choices of allocation methods and co-product handling. It's going to really lead to very different conclusions, right? So the y-axis is kilograms of CO2 equivalent, which is the unit for climate change impact per kilograms of your lignin, right? So as we can see, it ranges from like 4.0, where lignin is the main product, and then to another case that I'm going to talk about shortly. So it's a very wide range here, and usually when you have a main product, which like lignin, I think there are two very common ways you're going to allocate between lignin and let's say pulp. The pulp there. So one option is mass-based allocation. You just allocate the impact based on mass between the two products. And then another option is economic value-based allocation. And if you look at economic-based allocation, you already see the variance, right? So you have to pick let's say a sales price of the lignin. So and this sales price can be volatile, right? So you already see some variation when you pick a different method and they make a different assumption. And then if you apply what's called hybrid allocation method, for example, you can first allocate all the energy consumption between two products based on their energy use efficiency, right? And then you allocate a mass-based input, like chemical use, other material use between these two products, again, based on their material use efficiency. So this is a hybrid allocation method that's less commonly used as compared to mass, like solely mass or solely like economic allocation. So this kind of further kind of complicate thing, right? And then this is basically you partitioning your impact between your main product and the co-product. Then if we kind of like switch to a different lens, in this case, you expand your system boundary where you include your co-product as part of the analysis. Then what you're going to do is not separating the burden between your main product and co-product, but try to see how your co-product can replace certain products to give you some kind of credit, right? Then this is where you see a very different value here. If we assume the pulp is going to be used to replace cotton in a sanitary product, it will actually have a negative, very large credit in terms of carbon emission. And then, of course, if you choose another option, which is kind of interesting, is replacing the use of tablets. So you can, I think the author assumed there's certain piece of paper you can produce, and then there's certain amount of information you can read, and then compare it to reading it on the tablet where it uses, of course, like electricity, you will have certain credit, and then there's your overall net climate change impact. So all you can see here are different dots, different results, and based on the choice of allocation method and assumptions associated with them, right? Each of the options is actually legitimate, valid, depending on the scope of your research. So the recommendation, when you want to do a allocation, in many cases you have to do an allocation for a multi-product LCA when you calculate the carbon intensity, is that we really carefully select methods. And sometimes it's not one method based on the goal and scope of the study. For example, does your lignin actually serve as a precursor to a chemical, or it's kind of like a like a fuel to reduce your reliance on the external fuel like supply to your meal, right? So it really depends on your goal and scope, and sometimes and oftentimes you need to conduct sensitivity analysis to show the degree of variation or results from the different choices. So that's the allocation and co-product handling. And the next issue I'm going to talk about is about missing data, right? So I think for all the modelers, we know that for almost all models, it's like garbage in, garbage out, right? So your model really relies on high quality data. And whenever you have a missing, like a data point or like missing type of data, it's going to actually, in many cases, severely impact the output of your model. And then there are actually different situations when you conduct LCA to calculate, let's say, the carbon intensity of your bioproduct, right? So the one type of situation is that you know the existing technology, but they're just not available in the database. And I think as LC practitioners, we ran into this situation almost every day, right? So when you put a chemical in a search box and in your software, and it often returns 0 results. So that's a very common situation. You will have missing data. And then another situation is when you try to model some emerging technology, like a lot of the technology we're developing at BPI, is that you only get the data from the lab or like like small scale experiments, right? And then you really want to understand how the technology is going to perform, what's its environmental impact if it goes to the commercial scale. So this reflects the change of what's called technology readiness level, TRL. And these are the two very common situations you will have to handle missing data. And in the next few slides, I'm going to introduce a couple of approaches in the literature that you can actually take to address different situations. So the first category of approach is called mechanistic approach. And this figure, let me see. This figure has a really nice summary of different approaches you can take, especially when you're dealing with like chemicals when you're producing, right? So from top down, the very top section says getting plant data, which is basically you collect the data of a like a commercial plant for a particular technology. Then you get the most accurate data, right? But at the same time, it's very time consuming and in many cases impossible because of the cost, cost and the time and all that. So oftentimes you will go down a little bit and just run process simulation, especially if you're again producing some products or like a chemicals and you know the thermodynamic condition of the process and you understand chemistry, then that's a very powerful tool you can use to generate a missing data. Let's say the electricity used for your particular process when it go up, right? And then if you don't really have the access, let's say to those very sophisticated chemical engineering software, and you don't really have a lot of knowledge in chemical engineering, and then there are other options. For example, the process calculations is a category of methods where you basically rely on other people's empirical equations when they estimate, for example, the energy consumption, the heat use for a distillation column, right? And then if you don't really have this type of information, then you pretty much have to rely on the theoretical information you get. Let's say you know the chemical synthesis route for your particular chemical you're looking into, then you can rely on the stoichiometry of the chemistry, like the reaction, and estimate, let's say, the enthalpy of reaction for utility use, right? And also sometimes you can actually rely on the molecular structure models of the chemicals to estimate some of the like the reaction conditions you need. And the last two options is pretty much run out of options, right? You don't really have the empirical or exact, like the simulation data, you don't have the theoretical information, then that's pretty much your last resort is to pick from the database what is most similar product you can use. Like in many cases, when you do LCA, you have an organic chemical that you don't really find in the database, and then you run out of options. One way you can do is choose a industry average organic chemical in a database used as the proxy, which of course have very low accuracy, and you have to account for uncertainty, right? And the last option is of course to submit missing data, but we don't really want to go there. So here I have two examples about different approach we use in our own study. So there's this particular paper we published this year is actually looking at the potential of electrocatalysis, this kind of reaction for chemical and fuel production as the option to like mitigate carbon emission of the industry, chemistry industry. So the particular technology we look at is the catalytic oxidation of the crude glycerol you get from making biodiesel and make that into lactic acid. So this is I think a very typical Excel spreadsheet you'll get if you work in a lab developing the technology in the lab, right? So you will have, let's say, a bunch of the information about the main and the co-products when you measure your experiment, and you of course you know what is the amount of reactants, the chemicals you put in there, and the experiment conditions. Those are the information you can get pretty much all the information you can get from a lab experiment, right? And then what we really want to know is if we scale up this technology, is there any place where we can actually say, save some energy, right? So because in the lab, you don't really account for, let's say, heat recovery and all that. So what we did is that we used SM+ to simulate the reaction itself, as well as the separation of co-products, the purification, and then you get the lactic acid and recycle the glycerol and the heat integration through pinch analysis to actually reduce the utility use and all that. Then what it gives us is this is a typical lifecycle inventory table. Is, for example, the process electricity used, right? So we don't really have a very I won't say very accurate, but like close to real life number for electricity production if we don't run the simulation. So that's one situation. If you remember that triangle, that's the process simulation approach you can use to generate the missing data you don't actually have from your lab scale experiment. And another example is the recent paper we looked at LCA for the isolation of lignin-containing cellulose nanocrystals using the DES. And what we did is we kind of like work with our professor at our own department, and then we look at this particular situation where you have the thermomechanical flow and the mixed with the DES under certain temperature and for a certain period of time, and you separate them, right? So you get your LC and C. So this is a vertical representation of the process. And for an LC model, what you really need is the energy, right? Material, in this case, water, and waste generation that you can use to model the environmental impact of carbon emission. And what's different from the experiment, if you look at the upper right corner, is that in the lab we don't really recover DES, right? So, but in the commercial scale, in the full operation, you do need to recover DES. So here we propose a hypothetical recovery routine where you use ethanol to precipitate the DES, and then in this case you have to evaporate the ethanol and recover the ethanol itself, right? So in our case, we need to calculate energy demand for this particular technology, which is electricity and steam, which actually exists in the database. And then we really need to understand how the DES recycling can be modeled, which is not in the database. So again, this is the lifecycle inventory table where you can see we have a row for the energy for DES recovery. But in this case, we didn't run a SM+ model, but we just we use another category. If you again remember that triangle, there's a kind of like section called process calculation. So we use this approach where we look for specific information to calculate the heat consumption during distillation, and then we plug in the numbers, the conditions of our ethanol evaporation temperature and pressure, and then we get the heat consumption, right? So that's how we get energy. And then when we look for the chemicals, remember in many cases chemicals does not really exist in the LC database. So unfortunately, all the chemicals we want to model, I mean, none of them actually exist in the database we use. So what we did is that we go back to basic chemistry and look at how those chemicals could possibly be synthesized using chemical reaction. Then we look for the enthalpy of formation for each of the chemicals, and then we calculate enthalpy of reaction and of course sensible heat for the reaction and all that. Then by doing that, we actually get the energy consumption data for making those chemicals as well. So this is again another example of how you can actually get missing data using different approaches. So so far I covered mechanistic approaches basically, and you need to understand what's going on. You need to understand mechanism of the reaction, for example. But in many cases you don't really, right? So especially if you're facing a very complex system, you only have the data that, for example, your experiment measurement, and your experiment condition, and your yield, but you don't really know what's going on in between these two things, right? So then in this case, you can use what's called data-driven approach, and in many cases, data-driven approach is based on correlation, right? So mechanistic approach is more based on the causation, and the data-driven in many cases is based on correlation between two sets of data. So this is the example where you apply machine learning. In particular, this is a artificial neural network model where you have the input. So this is basically predicting yield of a biochar generation. So you like in this case, you know your raw material, like you can do the measurement of the the carbon content. You can also you of course know the activation condition where the temperature and time you for your experiment. Then by collecting a large like pool of sample data, and then you can create this correlation between the input data, which are all those attributes, and the output, which is the yield of the biochar generation. So this is an example of applying machine learning as one of the data-driven approach to estimate the missing data for your LCM model as well. So yeah, I think I'm kind of running out of time, so I will quickly like skim through my presentation here. There's another topic I would like to talk about is land use change, which itself can be like a 1 hour presentation as well. So quickly just go through what land use change is that let's say we have a cropland which you grow like crop food, and then you have forest land, right? So then direct land use change means that you take part of the forest, let's say, to produce biofuel crops, and which is kind of straightforward. And the indirect land use change is a little bit tricky, is that you take part of the crop you grow for food and make that into biofuel, then you need to compensate for that. So you kind of like open up, let's say, do the deforestation, and you open up the land for crop growth, which on the surface is not relevant to the biofuel, but it's indirectly affected by this biofuel, right? So that's land use change, and I think I'm going to skip this. And then for the recommendation of modeling land use change, I think there are a couple of tools you can use. But in the US, there's a tool called a CCLUP where they have the pre-calculated vectors you can use if you're modeling biofuel in the US. And for the biofuel production in Canada, typically there's a typical assumption, kind of safe assumption, there's no direct land use change, for example, for ethanol wood pellets. But there are some direct land use change values if you want in the tool called GHG. I think I'm gonna probably just stop here.